My name is Victor Lazaro, and I'm working as a R&D manager in a small company called Chemplate Materials. This company is located in Barcelona, Spain. And besides other business activity, we have a department that develop new technologies and manufacture equipment for the PCB industry. And in particular, the technologies and machines that we develop and manufacture are for the layer-to-layer registration and lamination. We have a few technologies that we have been developed from the past almost 25 years already. Probably some of you knows the induction bonding heating for layer-to-layer registration. But in between others developments, I'm here today to present a new technology and machine that we develop for lamination, okay? Which is the name of the technology that we put is X-Press technology, okay? So let's go into a little detail. What is the X-Press technology? The X-Press technology basically is a different way to create the heat, the thermal energy that the laminates need to be cured. Okay, the difference is that we don't use big thermal oil heaters, we don't use steam, we don't use electrical heaters, we just use induction. So on the next slide, the question is, what is then the X-Press novelty? Okay, so what this technology that we develop it makes is that we produce the energy, the thermal energy, the heat actually, right direct into the separator press plates of the press stack. So we don't heat up the resins or the materials to cure indirectly. We basically we heat up right at the PCB. So in fact, I'm going to go in detail how this works in a principal way, but I would like to show here a very good picture of this difference. Okay, when you go to a standard lamination presses, no matter the system it uses for heating up, you are heating up from outside to the inside of the press stack. So sometimes you have a multi-opening press machine, but nevertheless each opening have a big mass platen where you put in between your material. So that thermography, it is just the section side of one of the platens, where you can see that is being heated up by the oil heaters or whatever standard system. And then here you have your press stack that can be only 1 panel or maybe 10 panel high. Okay, so this is the distribution. So you have heat coming from the platens, and also the side is the mechanical guide of these kind of presses. The thermography on this new technology is all the way around. You have the heat created internally right at the material, so we don't have any big delays lag in between what is produced the energy and the material itself. So you have the same 10 panels high package here, and you can see here on the transparency that the top and bottom plattens are cold. They are not being heated up. But internally you have these 10 boards, 10 panels high, all together being heated up very uniform. So just wanted to make here kind of a big overview or summary of the main features of this technology, which is that we can get very high temperatures or extremely high. Actually, we have a test in the laboratory where we were able to fire alumina or ceramics. But for the printed circuit wall application, where right now for those high frequency speed PCBs is needed those fancy or very modern substrates or laminates. So those laminates require sometimes high temperature. Then, because that way of heating up, we can have a very high ramp up rates. Then the efficiency, energy efficiency is very high because we are not heating up the whole machine mass. Typically, when you go into a lamination room in a shop, what you see is that the room itself is hot, maybe as hot as outside now. But that means that a machine that have to apply a lot of pressure and it have to create energy, it is a big mass machine. And if you connect mechanically where the heat is produced to the whole mass, you are heating up the environment as well. So it's a big amount of energy that is being wasted out. Not to talk about the fact that you need to cool down the room if you want to survive inside. Then the machine can be elegant or not, depend on your flavors. And then we use a minimal space because we design a very compact unit. All right, let's go to the principal functioning of the system, of the heating system. I would like to move you probably back to the first year of engineering. So this is a kind of a basic on physics. But what we use is there is a big coil inside the machine where when you connect that coil to an AC current, if you supply an AC current here, what happens is by the electromagnetism laws, or Savart law, it creates a magnetic field around. This is something that everybody probably recall now. For those that maybe don't know much about, the magnetic field is this thing we cannot see, but you can feel when you face to two magnets. So that force is the magnetic field. So that magnetic field or that phenomenon is reverse, meaning that the same way you apply an AC current into a coil and it creates these blue lines which are the magnetic field, if you align properly inside that magnetic field another coil, it creates the current, okay? Then if we go also into this basic sketch or explaining the principle, going back here, this is the secondary coil that I was talking about on this reverse effect. And if we go to this secondary coil again on this next slide, instead of having a proper winding or a coil inside, if we put the separator plates, which is those yellow planes here, actually, because they are electrical conductors, they are working as one single turn in short circuit inside that magnetic field. Okay, I don't know if this is too clear, but if anyone have any more questions later on, we can go there. So nevertheless, what you can imagine now is if this is just your press stack package, okay, where in between the yellow planes you have your single panel or PCB. Now, just on a principal functioning application, how this all together can be put into a machine or a device that works freely instead of this kind of scientific information. So you have inside your press stack exactly the same that you have in your standard machines. But now, because we produce the energy right at the press plates, like if they were a single platen opening, okay, we now are able to put inside temperature sensor. Okay, so if we put inside a temperature sensor, and this temperature sensor is right inside the material itself in the resin, we actually can have the information, the real-time temperature of the laminate, not the plates, not the platen, just the laminate. Okay, and then if we put all these together in a block, flow block, what we have is a power supply and a control system with a PC where the feedback is coming from the real-time temperature of the material, and now it's possible to track perfectly profile temperature and deliver the energy real-time to the material. So we don't need to go from empirical system like today's system is, where you need to play with papers and isolators, otherwise your first panel on top is having a different thermal shock. So I'm going to go quick because I just have 10 minutes more to go. But here is more or less a sketch, a cross-section of the simplicity of the system. So where you have a cold plating, multiple, let's say opening, but in reality it's just the same press tag, where you have a multiple panels. The green color is the panel, and then that little thing in between is the press plate, and then you have a dummy panel in the middle with the thermocouple inside embedded. We create the heat internally. So let's go quick to the next slide, where you can see the traditional, what you guys are all familiar with, where you have a multi-opening. This is just 2 opening, but normally it's 4, 8, or whatever is the number. Basically, you cannot put more than, let's say, 3 to 5 panels high if you are doing high-end panels. If you do low-end panels, maybe you put up to 10. But the more panels you put in the side, the bigger is the delay of the temperature, because you have the thermal transfer coming from the hot platens to the material. So now, if we recover the slides of the thermographies, then you can see now or understand better the difference. Then I'm going to go quick on this. In reality, this is just an example of the energy efficiency, okay? There is a lot of things that it takes in consideration here that I removed from the example because I just want to simplify. But what I did here basically is just I wanted to heat up the same masses, okay, with just 1 panel. And with the traditional press, we got 1.6 megajoules for heating up the hot platens and the panels. And for the X-Press technology, we have much less, because the mass that we need to heat up is way less, basically as that. Okay, here are a quick view of the pros and cons of the technology. Basically, small masses to heat up that considers low inertia, so high temperatures uniformity. Press tag inside the temperature generation on each panel, so no thermal delay. This is very important. High temperature and thermal increase are possible. Direct or real-time temperature control, all panels are homogeneously heated up at the same time. Higher lamination repairability. This is a very important thing to improve process issues and higher process stability. So the repairability is high on lamination point of view. A compact design, high energy efficiency, we talked about already, and a low operation production cost due to energy savings, and is a green system. So no oils, no this kind of maintenance. So if anyone have any doubt, the press tag construction is exactly the same as today's one. So we use a standard stainless steel separator plate, so nothing special in the system. So you can continue using what you have already on the shop. And here is a view of the dummy panel with the 4 thermocouples. This panel is exactly the same material as the other panel that you're laminating. And then everything is programmed very simple into software, so you don't need to make the trials or the forerunners to check how is the temperature in the panel, if is the lamination good or not. So you basically follows your supplier material requirements data sheet, and you program exactly the steps of temperature they want for the laminate. And this technology is allowed to very, very accurate track the energy that you need to deliver each given second. So here is a little bit of a layout, Okay, this is kind of a standard but compact. This can be automated or not. This is the compact press, a little electrical cabinet, and a computer. So all this flow distribution. And I have here a video, if you please play, where we can see a 3-hour cycle in a very quick speed mode in 1 minute. I think it's accelerated, because I would like to show you how accurate the material tracks the thermal profile. This is, I don't remember the material, but this is the pressure ramp up that can be fully programmed in just one step up or in a ramp. The yellow line is actually the temperature that you want in the laminate. The whole stack inside the machine is getting this yellow temperature. You can see here the number in degrees, and here you can see the modulation of the power supply. So you keep all the time the temperature. Here the green line is the vacuum. We have also a high vacuum levels. In this case we are in a 15 millibars only. And yeah, the blue line is just the cooling part of the cycle. So here is what the way we cool. This is exactly also very quick. The outside is the ambient temperature, and this is the 200 degrees panel. So this video represents the natural way of cooling down, or the best way to cooling down a material, which is just keep it on pressure, open the window of the door of the press, and leave it there until he get balanced with the environment. So that is more or less what happens. I mean, you have the panel here in the middle. This is the press plate, and the only part of the material that are in exchange with the environment to exchange the energy are just the edges of the press plate. So what we did for cooling, for the cooling cycle, is we emulate what is, we believe, the best way to cool down a material when you open the press and leave it there in the environment under pressure. But we accelerate that. So that's why you see here some fans at the edge of the press plate. So we put airflow in between, so we can exchange the energy from the center to the outside on a very uniform way. So this is more or less an image of what I was just saying now. So you have a press stack. Obviously, the scale is not fitting, but it's just for this purpose, where you have your stack up with the panels in between. So we create, with an air exchange, we create an airflow that flows through the edges of the press stack, and then that air becomes hot because they are getting the energy out the panel to the edges to make this natural exchange. And then that airflow is passing through the air exchange, is being cooled down and push it again through the package. So that's the way we cool down. So here is press lamination main features. It can be to a very high temperatures at the moment. And yeah, I think you can go and check on the presentation, or if you need more details, just please contact. Here is some data, real data from Panasonic, for example, but we do have also from ITQ or Nanya or other suppliers. The lamination is very good. You can see here the TG is very, very tight. Also planarity. This means the thermal distribution is very even. The press can be used for standard things, can be used for fast cycle, can be used for advanced materials, or can be used for developing new process materials, because it passes the limitations of the traditional heating or systems that exist today. Anyway, I think I'm running out of time. Thank you very much for the invitation, of course.
When do you think is the breakthrough in industry? Did it already take part? Did it already happen, or when will it come for your specific technology?
Well, the technology that I just present in reality is working for already 7 years in a local customer. We keep it on secret, obviously, for the big potentials of this technology. And right now we already got a big order for a good customer. So I will say that there is always room for improvements and fine-tune process, but is industrial already in our case.
Is there any comparison between the press cycle time between the traditional and Express?
Yes, we have data on that, and it can be shorter. And I say it can be because there is a time needed for the process engineers to really understand and trust in the technology. But on the theoretical point of view, where we have the data, is that the resins let's say that there are parts in the temperature where the resins are not being affected by a high speed rate in temperature rise. So for example, from ambient room to 80 degrees Celsius, eventually you could go in just 1 second because the resin will not change any properties. So in the standard presses, you need to be adapted to, first of all, of the big delay lacking between the hot point and the material itself, plus the limitations of the big masses to be heated up. That needs a lot of power. In our cases, as we can have a very big or high speed rates, we could short those sections where the resin is not being affected by the high speed rate. So we have standard effort for the cycle time. It can be short as a 3/4 of an hour, half an hour minimum.
Regarding the Express, you say that initially it's the metal plates what are heating mostly and make the heating for the whole PCBs. But does the copper distribution somehow affect the heating distribution inside the packet?
Well, is this not as far as we know on the data we have, there is not any effect because the mass of the separator plates is way bigger as the copper. So that separator plates, it is balancing. You have a very good uniformity because the thermal resistance is very low. So there is no affection.
Victor, do you have any information about the temperature uniformity you will find within a panel and in between the outer and inner placed panels?
Yes, actually that was one of the key points of this technology. I explained it into the presentation, but I had no time to go in detail. But the press stack is uniform in respect to the magnetic field that is created inside, meaning that all the press plates are equal, exactly the same size and thickness and properties, mechanically speaking. So the magnetic field penetrates in all those separator plates in the same manner, with the same, they're very even, absorbing the magnetic field lines. So that tells that it creates exactly the same energy, the same losses into each plate. So answering about the temperature uniformity into a panel, any panel, it's within the plus minus 1.5 degrees, meaning biggest delta is 3 degrees in between the cold and hottest point over the surface. And to the other question about on the high, meaning that if the first panel is same as the one in the middle, it's exactly the same for the same question. There is, of course, in our system, a cold plate instead of a hot platen that could eventually store energy, right? But we have active thermal barriers that blocks that thermal escaping, let's put it that way. So we have also temperature sensors that compensate that, and we have exactly the same as any panel on the middle.
This means you have some kind of isolation material in between the outer sus plates and the cooling plate?
Well, there is isolation because you need to put, or normally on the PCB industry, they put a cushion for pressure compensation. Those materials are isolated. But I'm talking about much more the isolation in between the big mass of the press, which is the platen, the heavy thing, and the material in contact to the first and last panel. They are very actively and passively isolated.
Thank you.